this is a presentation on time dilation by me. So, oh my days. Safe, nice. So a little bit of like backstory on time dilation. Okay, I can't know anything about that, whatever. So time dilation is like an effect of Einstein's theory of special relativity, which he published a paper on 1905 titled On the Electrodynamics of Moving Bodies. So in that same year he published another like 4 papers which were all quite important to like different aspects of physics. Examples include the particle nature of light, or which is also known as the photoelectric effect. A paper on Brownian motion, a paper on E equals mc squared, and a paper on measuring the size of atoms. And it's known as the miracle here for Einstein. Newton had a similar one. So the thought experiment for which we're gonna derive time dilation from is this is Bob. He's located on Earth and he has a special clock with him. And then there is Alice in her spaceship flying past Earth. She also has like a special clock. So we're gonna imagine that at every single point in space there is a clock. No, there is a photograph which you can use. Both people can use to take pictures and measure the space location and the time location. Of like each other. So, and we're gonna have for our thought experiment as an assumption, we're gonna say that Alice passes by Bob when t equals 0. For simplicity purposes. So before we get into it, we got some background check. So time dilation was based on the special theory of relativity was based on 2 principles. So the principle of relativity, which stated that motion is relative and that everything is moving with respect to something else. So for objects moving in a constant velocity, there is theoretically no way to tell whether somebody is moving or not if you remove all external stimuli. So for example, think of when you're crossing the English Channel using that train. When you're in the train, you actually have no idea whether you're moving or not. Apart from sound maybe. And the second one is the principle of light constancy. So light is a wave, and most waves have some medium in which they travel in. So for example, waterways have water. When that medium moves, so if you have like a trough with water and like a paddle that generates water waves, if you move the trough and the water like on a skateboard, let's say, when the medium moves, the velocity of the waves and the velocity of the medium will add up. So, however, light does not travel through a medium, so we assume that its velocity is always constant at 300 kilometers per second, which is also represented by the letter C. Now we'll get into the actual things. So this is a light clock. So it is comprised by 2 parallel mirrors with a distance L between them. Between the mirrors, a light ray bounces from one mirror to the other, and we define the tick, one tick of the clock as the time it takes from the light ray to get from the bottom mirror to the top mirror and back down to the bottom mirror. So that's 1 tick of the clock. So as mentioned earlier, Bob is stationary on Earth and Alice is moving past him. However, from her perspective, or frame of reference as is the scientific term for it, Alice is stationary. So she does not see her clock. She does not see her clock and herself moving. She only sees Bob traveling to the left of her. So this is Alice's clock as she sees it. Obviously, it's it's what I explained just now. The light rays bouncing up and down the mirrors, distance L from between them. However, Bob, who sees Alice traveling to the right, is gonna see the mirrors move like this. So the mirrors are gonna be constantly moving. And the light ray has to travel diagonally from one mirror to the other, because if it doesn't, it's gonna miss the mirror, and therefore Alice's time from Bob's frame of reference is gonna stop ticking, while Alice's time from Alice's frame of reference is gonna continue ticking, and that's a violation of the principle of relativity. So yeah, these are like 3 snapshots of Alice's clock in Bob's frame of reference. So we have one where it's just snapshot 1 where just the light just starts leaving the bottom mirror. 2 is at some other point further to the right when it meets the top mirror, and then 3 is even more further to the right when it completes the tick on the clock, and it meets back down with the bottom mirror. Anyway, we can, as you can tell, obviously, the time it takes for light to get from the bottom mirror to the top one and then back down will be different in Alice's frame of reference and Bob's frame of reference. But just how different is the question. Also, I forgot. We can define. We're gonna say that one tick of the clock in Alice's frame of reference is delta TA, a capital T for tick, and delta TB for Bob's frame of reference. Delta TB like for the one tick of the clock in Bob's frame of reference. We can use the equation speed equals distance over time and rearrange it to get time as distance over speed. And obviously the distance is 2L. So double the distance of the distance for light to get from here to there and back. So it's going to be 2L and divided by the speed of light, which is c. So yeah, we defined delta TA as 2L divided by c. The equation for delta TB is a little bit more complicated. As the clocks move, we're gonna have a diagonal distance that light travels, which is the actual distance it travels, and then we're gonna have the horizontal distance that the bottom mirror has moved throughout the duration of the tick. So we can rewrite x as delta TB times v. So this is the distance, and distance is equal to time, which is delta TB, times velocity. And then we can use Pythagoras' theorem to get that d squared equals L squared plus x divided by 2, which is this distance here, like half the distance the bottom mirror will travel in like the direction of a tick, squared, of course. And our aim is to substitute delta TA and delta TB for these letters so that we can get a relationship between the two. So when we do that, I also forgot to mention that we can rewrite D as delta dB times C divided by 2. So when we substitute in for these values, we get this equation, delta dB times C divided by 2 squared, and then delta TA times C divided by 2 squared, and then I forgot to rearrange this again. So remember how we said that delta TA is equal to 2L plus C, 2L divided by C? We rearrange this to get, let me do it over here. So we have delta TA equals 2L over C. We rearrange this to get L equals delta TA.
Isn't it 2D over C?
Sorry?
It says on the board that it's 2D over C.
No, L is equal delta.
Oh, okay.
Yeah, that's sorry, let me just write that a little bit more clear. Yeah, so we're using to get delta TA times C divided by 2. Then for delta TB, equals 2d over c, is the distance that light will travel from here to here and from here to here in that certain amount of in the distance light will travel in the speed, that certain distance will travel in the speed of light. So we rearrange that to get delta TB times c divided by 2, d equals. Yeah, so as I said earlier, we substitute all of these into here. So we end up with this equation, and then if we expand everything, so expand and simplify everything, we will end up with delta TB equals delta TA times a certain number, which is times 1 divided by the square root of 1 minus v squared over c squared. And this over here is known as the Lorentz factor, which is which we use gamma for as a symbol. So we know that delta TB equals gamma times delta TA, and then we can use this to find the relationship between the time elapsed. So this is like a simple diagram. So if we assume that the value of gamma is 4 and that the duration of each clock is 5 seconds, we have one tick. No, this means that as gamma equals 4, it means that for one tick of the moving clock, we're gonna have 4 ticks of the stationary clock. So this is one tick of the moving clock, and until the moving clock ticks again, there are gonna be 4 ticks of the stationary clock. So this is gonna take, so one tick is gonna take 5 seconds, and then 4 ticks here are gonna take 20 seconds. So we know that delta times the time of a moving clock, which we define as the clock that is moving in the observer's frame of reference. So in this case, the moving clock is going to be delta TB, and then the stationary clock is obviously a clock that is not moving, so that's going to be delta TA. So we can find the relationship between them. So delta T stationary is 5, as I said earlier, like one tick of the clock, and then sorry, that should be a capital T. So 5 seconds elapsed in one tick of the moving clock is going to equal to 20 seconds elapsed in 4 ticks of the stationary clock times another factor y. Z, sorry. So 5 equals 20z, z equals 5 over 20, and so z equals a quarter, which is the same as 1 divided by gamma. So the equation for time dilation is that delta t in a moving clock is equal to 1 over gamma times delta t stationary. That's the equation for time dilation. I imagine it was like quite a bit to get through, so before I continue, does anybody have any questions?
Yeah, go back on the previous slides, please.
This one?
Yeah. So you wrote 5 equals 20y. Where's that y come from?
Yeah, sorry, that was a mistake. It's supposed to be 20z.
Oh, okay.
So yeah, that's my bad, sorry.
Oh, and you compared. You said that light doesn't have to go through a medium to just travel.
Yeah,
So
it travels through a vacuum, yeah.
So are you saying that time doesn't have a medium to travel through as well?
Well, time is not a wave,
Yeah.
so time does not travel through something.
So what's the relationship between time and light? Because you talked about the principle of light being compared
The
to
principle of light constancy.
Yeah.
It's that the speed of light is constant for all observers. Sorry, I did not make that clear earlier.
So it's between like speed and time, right? That's the relation, not between light and time. Because it's the speed of light.
Yeah.
Yeah.
Oh, yeah. Sorry. Yeah. That's one. My bad. Any other questions? Do all of you like follow everything?
So the principles were used to talk about the light clock and not about time.
Yeah.
Okay.
Yeah. Sorry, that's my bad. Okay. Do you guys want me to move on?
Yeah.
Solid. Okay, so the conclusion from that's a quick slide about what the value of gamma implies depending on v. So if v equals 0, so if both clocks are stationary, then delta Ta will equal delta Tb as gamma equals 1. So if we look again at this gamma over here, it's v squared over c squared. If v equals 0, then this whole thing will equal 0. This will be square root of 1 is 1, 1 over 1 equals 1. So the minimum value gamma can have is 1. And then for values of v between 0 and c, gamma will take a finite value bigger than 1. For example, when v equals 0.5 c, gamma will equal 1.5. When 0.99999 c, gamma will equal to 223.61. For v equals c, we'll end up with a division by 0, so this will end up being 1 over 0 for v equals c. And this sort of implies that the speed of light is the natural speed limit and that no object with mass can reach the speed of light. So in conclusion, moving clocks run slow. So a moving clock, a clock that is moving from the observer's perspective, will run slower than an identical stationary clock, which is a stationary clock in the frame of reference of the observer. This is known as time dilation and is true for all special cases where an object is moving at a constant velocity, hence the name special theory of relativity. Also, a quick fact, the frames of reference where the objects are moving at a constant velocity are known as inertial frames of reference. So, what about non-inertial frames of reference? So time dilation for the special theory of relativity works only when the object is traveling at a constant velocity. For when that is not the case, Einstein came up with a new theory, and for that I'm gonna introduce you to the equivalence principle, which states that an accelerating frame of reference is physically equivalent to the acceleration experienced in a gravitational field. Question?
I was just wondering before we go to acceleration, I kind of got what you said, but I don't really understand about why the speed of light is
Constant.
Oh no, speed of light is the maximum any particle.
All right. Yeah. So.
Because I just didn't understand how physics is going.
Yeah. Sorry. Okay. So let me write all of this. So we said that we found out that this, right? We derived this, and we know that gamma equals 1 divided by the square root of 1 minus v squared over c squared. So take v to equal c. So for v equals c, we're gonna get 1 divided the square root of 1 minus c squared over c squared, which is equal to 1 divided the square root of 1 minus 1, and eventually we get 1 divided by 0, which is undefined mathematically. So it's an implication that no object with mass can travel as fast as light. And so far it has been proven to be correct.
Yeah, okay.
Yeah,
that makes sense.
I see. Okay, so let's go back to the equivalence principle. So yeah, the equivalence principle says that an accelerating frame of reference is physically equivalent to the acceleration experienced in a gravitational field. Einstein imagined a man falling from a building, and he realized that as he fell, he would not feel his own weight, meaning that he would not feel the force of gravity pulling him down. So yeah, that's how Einstein. So he realized that this was also the case when accelerating. Sorry, I did not explain this very well. So when you accelerate downwards due to gravity, you do not actually feel your own weight pulling you down. So take a rocket elevator for example. If you start accelerating upwards, so if the rocket is stationary, you will just float in space, given that the elevator is located in space because there is no gravity. But if the rocket elevator started accelerating upwards at a velocity of 9.8 meters per second, it would be the exact same thing as being on Earth, which has a gravitational field strength of 9.81 newtons per kilogram. So if you drop the ball on Earth, it will start accelerating downwards at 9.8 meters per second. If you drop the ball on that elevator, it would float, but as soon as the elevator started accelerating upwards with that 9.81 meters per second squared acceleration, the ball would fall down to the elevator with that rate as soon as you dropped it. Yeah. So this is a little bit more complicated, so I'll do my best to explain it well. So we have another hypothetical scenario. We have the elevator, and we have clock L, so the lower clock at the bottom, and clock U, the upper clock at the top. And then we have two light ray shooters, for example. That's how we're gonna call them. So they emit light rays from one side of the clock to the other, and on the other side we have light ray detectors. So if the elevator starts accelerating upwards, the distance that the light ray is going from the bottom to the top are gonna have to travel is gonna be greater compared to the distance these light rays are gonna have to travel to get from here to here. Do all of you get why?
No.
So go on,
Okay.
explain one more time.
So the elevator is moving upwards, right?
Yeah.
So let's say, so after a few seconds, the elevator is gonna be higher up than it began. So
So one of the beams has to travel less than the other.
exactly.
Yeah.
So one of the beams will travel less distance because the elevator is moving. So think about it. The rays coming down from the top of the elevator. They're gonna get closer and closer. They're gonna get the bottom of the elevator, and the light rays are gonna get towards each other because the light rays are moving downward and the elevator is moving upward. But the top of the elevator and the light rays coming from the bottom the elevator is gonna move away from the light rays, but because light is faster than the elevator, the light travels at a greater speed than the elevator, it's gonna catch up to the top. So effectively, the light rays going from top to the bottom are gonna travel a smaller distance. So yeah, again, let's say that when the elevator is stationary, the detector detects 10 light rays every 10 seconds, so a light ray per second. Obviously, if the distance these light rays have to travel is greater, a smaller number of light rays will be detected in the 10 seconds. Let's say 8. So as the detector will have detected only 8 rays, but the clock shows 10 seconds, it gives the impression that the clock is running ahead of what it should be. Because why would it not show 8 seconds since it's only received 8 rays, right? So, and then in the opposite case, for clock L will show 10 seconds, but because the light rays going downwards will have traveled a smaller distance, the detector here might have received 12 light rays. So instead of showing 12 seconds, which is what you would think it would show if the elevator was stationary, it will show 10 seconds instead of 12. So it gives a sense that it's running behind. So overall, So if we substitute again the idea of the elevator being a gravitational field, so let's say this is Earth, clock L, which is closer to the gravitational field, will run slow, run slow, and clock U, which is higher up the field, will run faster. So Einstein derived that when the objects that are closer to the source of the gravitational field, this is not really right because nothing produces gravity. And basically, when gravity is strong, the stronger the gravitational field near an object is, the slower that clock will run. So because clock L is closer, is at the bottom of the elevator, the gravitational impact of the impact gravity has on that clock will be stronger compared to clock U. So the time dilation effect will cause clock L to run slower and clock U to run faster. Bro?
How can we we've done this experiment theoretically with light rays, but how can we relate that to time? Why does this mean that the different seconds and stuff? How does the light have to do with time?
Because so where did I put the answer? Here. So okay. Right, so you have the elevator, right? The elevator. And the speed of, so the light rays start coming off here and here. And they're traveling at the same speed. Obviously, because the elevator is moving up, at some point, let's say a second later, it will no longer be here, it will be here. So you see how how these light rays have to travel a shorter distance.
Yeah.
So as time equals distance divided by speed, the speed is the same for all light rays, obviously. If the distance is greater, the time it will take the light rays to reach the detector is greater. So because this distance is greater than this distance, this is not very clear, sorry. The time it will take these light rays to reach this detector is longer, and in a certain amount of time, less light rays will reach this detector compared to if the elevator was stationary. And in the opposite case, more off. And in the
It's alright.
right.
Boys.
Wait up. Okay. So this, less light rays will reach this detector in a certain amount of time, and more light rays will reach this detector.
Right.
Yeah, question?
But you're only talking about gravity up and down, and we know that gravity is not just an up and down movements. What will happen to the light rays if the elevator went left, right, forward, backward, 360, or?
Gravity is not up. It's not upwards or downwards. It acts at all directions. But the important thing is that it acts at 90 degrees. So we have Earth, and then this is the center of mass, the center of gravity of the Earth. It will act at 90 degrees to the center of mass. So if you're here, gravity will act downwards this way. If you're here, gravity will act this way. So with respect to the center of gravity of a certain object, whether that is the Earth, the Sun, or a black hole, you're always traveling towards it. So it's not really that it's going downward. it's but it makes more sense if we talk about it that way. I suppose. And then in the case of the elevator, I know it's a bit confusing that the elevator is traveling upward, but if you think about it, you're a human floating in space inside the elevator, and then so you're not touching the elevator when it's stationary because there is no gravity. There's nothing pulling you down. But if the elevator starts accelerating upward, you will remain stationary, but the elevator will start getting closer and closer to you until it reaches you, and then from that point, you will remain stationary because the elevator keeps on accelerating. So it has the same effect as being in a gravitational field.
Okay.
Yeah, Brian? Yeah. That's it.